Hey guys, this is my fourth project deliverable for vibrations, and we're going to continue talking about the solution to the Jeffcott rotor model, and more specifically how the parameters play a role on the outputs of the x of t and y of t of your transverse planes of motion. So I have set up a control output with control output from Maple from our solutions of x of t and y of t. And these are from the equations of motions where mass is times the acceleration plus your dampening coefficient times your velocity plus your stiffness times your position. And all of this is equal to omega squared times your mass times your eccentricity and times cosine omega t for your x equation of motion and times sine omega t for your y equation of motion. So if you look here, you can see the transient regions and how it eventually becomes more at a steady amplitude towards the end at the steady state regions. And it's important to know the role that the parameters have on these outputs. For example, the diameter of your shaft is related to your inertia, and your inertia is proportional to the stiffness, and as well as 1 over L cubed being proportional to your stiffness. So all of these play a role in determining your frequencies. So a larger stiffness value will give you a larger frequency, and a larger mass value will give you a smaller natural frequency for your system. And it's important to notice the role of the dampening coefficient on your damped natural frequencies. And as the dampening coefficient goes up, your damped natural frequency goes down. And you can see that when we come to the point where we change our damping variable. So in this first comparison, the length parameter was increased from 10 to 20, and you can see that there's a volatile transient period. The frequency in world peaks is lower and they're less tight, and this is because as the length increases, it decreases the value of k, and therefore it decreases your value of both your undamped natural frequency and your damped natural frequency. So the next parameter that was changed was I changed the shaft diameter from 1 to 2, and you can see that in this that it reaches steady state much sooner than in the control, almost immediately, and that you can see the amplitudes are significantly reduced from the amplitudes of the control. And this just shows that increasing diameter increases the inertia of the system. So the next parameter that I changed was the mass from 1 to 2. And this lowers the natural frequency due to the increased mass, and therefore shows less peaks. And you can see that there's smaller amplitudes of the response peaks, but the transient period is pretty similar shape to the control. Now, this is an example of where the damping coefficient was majorly increased, and you can see that it reaches steady state oscillation much sooner than the control. And you can see that the output response of the amplitudes are much smaller, and that this is because as C increases, your damped natural frequency also decreases, and that's where the less tight oscillations come from. Now here's a case where the eccentricity is reduced to 0, and I set deflections for both directions on at +1 and -1, and you can see that this is just a normal damped oscillations in two transverse planes when there's no difference between the center of rotation and the center of gravity. And for this last case, I increased the omega by 5 times. And you can see that the outputs of the x of t and z of t functions are completely out of sync in the beginning, but still eventually reach steady state towards the ends as it approaches t equals 1,000. Thanks for your time. See you next deliverable.